Hello everyone, welcome to Physics Rocks It's True. In this episode we're going to discuss the structure of our solar system from the sun to the planets to moons, asteroids and comets. We're going to learn the order of planets, we're going to look at why planets continue to go around the sun, and then we're going to talk about how we use that in our modern satellite communication stuff. So let's get started. Alright. So here we have the solar system in all its glory. Now it's a little bit of a simplified view on this one, but we've got all the main parts that we want. Right? In the center we have the sun. Now note, this is ridiculously not to scale. Right? The sun is ginormous, and if you were to make this at scale you wouldn't be able to really see anything, because all you would see is this massive blob that was the sun, and then there might be some specks further out that would look like the bigger planets, and that's about it. And you probably couldn't fit it onto this screen, so it'd be a waste of time. So everything here is terribly not to scale. Please, please, please keep that in mind as we go through this. Okay, the structure of the solar system though is pretty logical in that we have the sun at the middle, which is a giant burning nuclear fireball. Then we have our four inner planets. Okay, they're called the inner planets because the inner planets and the outer planets are separated by this thing here, and this is called the asteroid belt. And we'll explain how that forms in a future video, but at the minute it's just like a pile of rocks flying about. The inner four planets are primarily made of rock. They're rocky planets. They have lots of heavy material, lots of iron, lots of kind of big atoms from your periodic table. Then there's bits and pieces, fragments left over that didn't make it into planets, and then out here we've got Jupiter, Saturn, Uranus and Neptune, the outer planets. Now these planets are made of gas, or primarily made of gas anyway, so they're less dense than the inner planets, but they are much, much larger. So because there's a lot more gas floating about than there is heavy stuff in the universe, there's more material for them to have built themselves over time, but they are less dense because by definition gas is less dense than solids. Okay, out here we have random little things going around. These are called comets. Now you will notice that the planets are going in roughly circular orbits. It's not quite right, they're slightly more squashed egg things, but they can be pretty well approximated to be circles. They go around nice and evenly and regularly in their orbit, going round the sun and round the sun and round the sun. The comet, however, is coming in an orbit that takes it way away from the sun, like well beyond the outer planet, and then back in, running really close to the sun, and then back out again. And this is what kind of eliminates us from a comet, from being a moon or a planet or something like that. There's this really, really eccentric orbit that goes long way out and then comes in close to the sun. Comets tend to be made of frozen ices, so like things like water. That's why they get a little tail, because as they're out here, way away from the sun, they're frozen solid in the coldness of space. But then as they move their way in and move their way in and move their way in, the heat of the sun starts to just like the moon did. Alright, not just quite like the moon did, much closer than the moon, but it goes round and round and round. Really, really quite impressively. We use this for all sorts of reasons. We use this for like monitoring the weather. We use it for GPS systems. We use it for communication. We use it for satellite TV. Okay, artificial satellites are extremely, extremely useful. Okay, so satellites fall into two categories: natural satellites, like the moon, and artificial satellites, like the ones that we launch into space. Okay, and that's what you've got. And the Earth has one natural satellite and countless artificial satellites. So why? Why do they work? Like, why does something go round something else in space? Because in space, there's no friction, there's no air resistance, there's no nothing. This should be an absolute heaven for Newton's first law objects, that an object will continue to travel at a constant speed in a straight line unless acted on by an unbalanced force. So away it goes. It should just be going straight. Okay, constant speed, straight line. But clearly, that's not true. Okay, once we get a decent sized star and our little planet comes somewhere near it, then the planet starts to go around that star. Right, now this is the very definition of not a Newton's first law situation. This thing is not going at a constant velocity because it's constantly changing direction, certainly not going in a straight line, so away it goes round in a circle. And therefore that means there must be an unbalanced force acting on it. And the force acting on it is the force of gravity. That the star is pulling the planet towards it. Okay? The gravity of the star is pulling the planet towards it. Like, oh no, that is terrible, I hear you cry. Because surely that means that our planet should just get eaten by the sun. But not quite, because our planet is going like bejesus trying to go at least like bejesus in a straight line this way. So what the gravity does is the planet wants to go along this path, but gravity pulls it in, so our planet doesn't get to go this way, but comes a little bit this way. Right? But once it gets around to here, the force of gravity is this way. But the planet wants to go slightly different direction this time. It wants to go this way. But the gravity stops it from going along this line, like this, and forces it to travel in this path. And it turns out that no matter where you go, that even if we're around here, our planet wants to go at a constant speed in a straight line. Fix that arrow. Our planet wants to go at a constant speed in a straight line. It wants to go this way, but it doesn't follow that path because the gravity makes it come this way. This is what we mean by centripetal motion. That things that go round circles are constantly falling towards the middle of this object without actually getting any closer to it. This is a stable orbit. And this will go round and round and round and round and round. As long as the planet keeps going at a good speed, it'll never get any closer to the star. And because there's not really anything in space to slow you down, you're going to keep going at a nice steady speed. So that's good news. We're not going to end up falling into our star. Far worse things are going to happen to us, but that'll be in our next video about how stars are formed. At the minute, this is why. Our planets go round the sun because of gravity. And we can absolutely extend this logic to our artificial satellite. That the force of gravity is trying to pull this thing back down to the planet Earth, but it's been launched in such a way that it's trying to travel in this direction. And as a result, as it tries to travel in this direction, it gets pulled inwards and it ends up going round and round and round. Now, if the time it takes to go round the Earth is 24 hours, it looks like it's sitting right above the same place. And that makes a geostationary satellite. Okay, geostationary satellites are really cool because they can be used for communication. And by communication, I mean sky television and like internet or satellite phones, things like that there. So television as well. Because when you look at your satellite dish or the satellite dish somewhere nearby, you'll notice that they all point the same way. They're all pointing to the same spot in the sky, and that's the spot where this satellite is sitting. Okay, but maybe I don't want to sit above the same spot. Maybe I don't want to go round the Earth. Well, there's another way of doing this, is the Earth itself is spinning. We know that. It takes 24 hours to do a day. I'd like to think that if you've made it to this channel, you know that the Earth is spinning. Right, it's not flat. We might do a video on that sometime in the future. Right, the Earth is going round and round and round and round and round. It takes 24 hours to do that. So if I want to monitor the weather or the surface of the Earth, rather than having my satellite go round and round and round the Earth, which is quite difficult to do and make it track all the bits, instead I make it go over the North Pole and round to the South Pole in a kind of arc like this. Okay, so what happens is as the satellite goes round the Earth spins below it as well. Okay, so it does like a loop every few hours. So it goes click, 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 takes all the pictures as it's going around this. You know, taking pictures, taking pictures, taking pictures, taking pictures, taking pictures of the other side. But by the time it comes back around here, the Earth has rotated on a little bit. Okay, the Earth has moved on to a little bit, so when it does its next loop, you get a different picture of the Earth. This is useful for things like weather monitoring. So these are called polar satellites. Get that right. And they're useful for things like weather monitoring. They're useful for tracking for tracking land, for tracking land masses. So things like we're watching how the polar ice caps are receding and stuff like that. We can weather monitor that. They're really good for things like spying. Right? You want to spy on a country, you don't just park a satellite above them. You can't see their whole country, first of all, and second of all, they take kind of badly to it. Whereas you just stick a spy satellite up and say, oh, we're tracking the weather, be grand. Okay, you can use both polar and geostationary satellites for astronomy as well, depending on what you want to do. You can, rather than point their cameras down towards the Earth, point them out to space and have a look at some stars. Okay, so these are uses of artificial satellites. So the last thing that we have to do then is come back to our very first graphic about the solar system and do the good old-fashioned naming of the planets for this video. Now the planets are in order from the Sun the following. The closest is Mercury, followed by Venus. Venus, interestingly, is the hottest planet, even though Mercury is closer. That's because Venus is bigger and has an atmosphere, and that atmosphere traps heat, whereas Mercury is too small, so its heat ends up just leaching out into space as soon as nighttime falls. Earth is next, so we're the third planet from the Sun. Mars then, our next great hope for getting ourselves off the planet, comes next. Then you've got the asteroid belt, and then you've got the giant of the solar system. This is Jupiter. Okay, the next biggest planet, or the biggest planet in our solar system. The only thing that even looks like it might rival the Sun, and by might rival the Sun in the same way a toddler might rival a heavyweight boxer. You know, it's just the fact that they happen to be playing the same game. Right, Jupiter next, then Saturn, then Uranus, or Uranus, if you particularly fancy the pronunciation like that, and then Neptune is our last planet. Okay, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now I like to have this one with my very early morning jam sandwiches, usually nauseate, even though I'm pretty sure that's not how you spell nauseate. There we go. That doesn't look right either, but we'll go with that. And that's us. So in this one we discussed main features of the solar system, order of the planets, gravity providing the force needed for all the stuff that goes on in the solar system, uses of artificial satellites, and why it all works. I will see you in the next one, and in the next one we're going to look at star formation, how the Sun formed, how all stars formed, and how all stars die, because they die differently. But for this one, if you like this video, hit the thumbs up button, I'd appreciate that. If you disliked it, put the thumbs down, but please leave a comment as to why and what I could do better. Hit subscribe, hit the bell notification for further ones, and I will see you next time. Ladies and gentlemen, please, please, please do not forget that physics rocks. It's true.